Hello everybody. In this video we're gonna do the derivation of the general equation for the mass transfer by diffusion, and we are gonna start with the basic, or the derivation starts with the basic concept of the conservation of mass. This is what the derivation is gonna start with. And before we start with discussing the terms, the mass in and mass out and all these things, we need to talk about the control volume first. And by the control volume, I mean the volume in which I make I do the balance equation. And this control volume that we have is a cube that has dimensions of delta x, delta y, and delta z. And it is a differential tube. It means that it is very, very, very small. The procedure that we're going to follow is we are going to apply the four terms, the balance equations, on the cube, and then since it's a differential tube and this is very, very small size or small volume, we will integrate it over a big area. And here, before we go through this, and I think this is something that we saw a lot in fluid mechanics, in heat transfer, and in reaction engineering, and in many chemical engineering fields, and in other fields as well. I believe the same is in electric fields and stuff like that. And what we see here is that we are starting with a differential volume, and then we integrate. And I think this might be a question that is jumping into your mind. Why do we follow this procedure? Why don't we directly go to the equation that describes or do the balance equation on a big volume and save time, instead of going for this small volume and then going to the big volume from the small volume? And the reason of this is when we talk about a system, in case of mass transfer, for instance, and this system is a big system where we have changing concentrations from one point to the other, we have change in temperature, in heat transfer, or whatever the parameter that we are interested in. If you have a change in this parameter over the whole volume or the whole area, the whole distance, whatever the scale that you are working on, then you will never be able to write an equation directly that describes the whole system, or directly to describe the whole system. And the reason is you have to use a parameter to describe this system. So if you apply this parameter on a system that has a concentration gradient, so you have very high concentration here and very low concentration on the other side. So if you apply the equation on this side, or on the concentration of this side, then you are assuming that the concentration all over the whole volume is the same. But this is not right, because the other side has lower concentration, and the same for the other side. If you apply it here, then you are assuming that the whole system is at this low concentration. And that's why you cannot write directly an equation that describes a system with a varying parameter, or what we call a distributed parameter system, that this parameter has a distributed value. And that's why you have to find a way that you can write the equation. But if for instance this system is a huge system, but it has a uniform parameters, that the temperature, the pressure, the concentrations, and everything is constant, you can describe it simply with an algebraic equation, because the equation will describe what is actually in the system, which is the same everywhere in the same system. So this is something that you can describe with an equation. But if it is distributed along the system or throughout the system, then it's not possible to write an equation to describe this system. So what we do is we assume that we have a very, very small volume, which is a differential volume like the one we see here, and this differential volume is very, very small, so that we assume the concentration inside this, or the parameter inside this cube or this volume, is homogeneous. And by doing this, you can write balance equations on it, because the concentration is homogeneous. And this is a very valid assumption, because it's a very, very small, it's a differential volume. We don't say x, y, and z, we say delta x, delta y, and delta z, because it's very, very small. And we will see in the derivation that we make, the delta x, delta y, and delta z are going to be almost zero, like when they tend to be zero. This is what we assume. And this is why we end up with a differential equation, because we are applying our equations on a differential volume. And this is why we have or we use integration to apply this equation on the whole system. And this is a very, very important concept, and I think it answers a question that many of us have, which is, why do we do integration and differentiation? Why do we study this branch of mathematics? And actually, this is the reason. If you are not able to integrate the equation and convert this equation from a very or an equation that's applied to a very, very small volume to an equation that can be applied to a big volume, then you'll be in a big problem, because still your derivation is fine, you're getting the differential equation, but you cannot use it, because the differential equation cannot be used by itself. You have to integrate it so that it's an algebraic equation. You can substitute and get outputs from it. So a differential equation is very useful, but without the knowledge of integration, it's going to be useless. And that's why we study differentiation and integration. And unfortunately, this concept is not taught in the mathematics courses, and you just start the math course with the integration and differentiation, and you do this to do integration, and you do this to do differentiation, and these are the cases, this is what you're doing, this is how you add to the power 1 and divide by the new power, and all these rules and equations and steps. But this concept is never discussed in math courses, and this is why I believe it's important to have this concept and understand it, and that's why I thought it's useful to take these minutes to describe this concept so that it is clear in your mind. Anyway, so the derivation is going to start with the balance equation, which is the conservation of mass. We said this is a differential volume, and we are writing the equation on a component A. So we're saying that the mass rate of A coming out of the control volume minus the mass rate of A going into the control volume, so it's what's leaving minus what's entering the system or the volume, and then the net mass accumulated within the control volume, the accumulation, how much is the concentration of A increasing, or the amount of A that's increasing or decreasing in the system or in this volume with time, minus the mass rate of production within the control volume. So these are the production is due to the reaction or whatever that is producing or consuming the component A. So for all these cases or for all these terms, this will cover any mass going in or coming out of this volume. So we can apply it for one species or two, or we can apply it to the whole flow. It's applicable to anything. So what we are doing or are gonna do in the coming slides is to see what can we put as a mathematical representation for each one of these brackets, and then put everything together at the end. So we will start with the first two brackets, which is the mass in and mass out. So let's assume that the mass is going in from here and coming out from the other side, and that it's entering at point Z and coming out at point Z plus delta Z. And this is how we are doing the calculation. So the first is the mass going in the control volume. So it's expressed as rho A, which is the mass concentration in moles per, grams per centimeter cube second. For instance, centimeter cube. It's mass per unit volume, so it's gram per centimeter cube, for instance. And then if you multiply it by the velocity of A in Z direction, which is this velocity, then you will end up with units of flux. It's going to be gram per centimeter square second. And then we are writing the balance based on mass, so or mass rate. It's not mass flux, so we are multiplying it by the normal cross-sectional area. So here for this direction, the normal cross-sectional area is delta x delta y. So this is how the equation is at point Z. The same would be the case for the mass coming out of the control volume at point Z plus delta Z, which is the other side of the cube. And it's exactly the same because we assume that there is a very, very minimal change. So we don't have any change in the rho that is obvious in this very small volume. But we say that this is at Z plus delta Z. And as we said, the rho multiplied by V is NA, and here we put it as NA, not JA, because but both are fluxes. We said before that the flux can be J or can be N, and we said the difference. And the difference is that the N is the flux relative to a constant point in space and or stationary axis, but J is the flux relative to the average velocity. So the reason we chose N in this case is because this and this are at point Z and Z plus delta Z, and the point Z is defined according to the point of origin. So this is a point that is fixed in space, a stationary axis, and that's why we have to put N that corresponds to this. So that's why we put it as rho A VA equals NA. The same can apply for X direction, Y direction, and Z direction. And then if we substitute in the equation for the two brackets, we can have it like this, or you can have it in the form of N as we see here. And now we can apply this equation for X direction, for Y direction, and for Z direction. So we can apply it for the three directions. And as you see, the main difference is that for each direction you change the area. So here it's delta X, delta Y in Z direction, delta Y, delta Z in X direction, delta X, delta Z in Z in Y direction, and it's the same. So this is for the first two brackets. Now the coming two brackets, the rate of mass accumulation or accumulated within the control volume, it's partial M partial T, which is the mass accumulated per unit time. The mass is the rho, which is the mass concentration multiplied by the volume. But in this case, since we have a differential volume, then it's the dV, which is the differential volume, which is delta X multiplied by delta Y multiplied by delta Z. So this is the expression for the mass rate of accumulation. The last term is the rate of mass produced due to the chemical reaction. So it is R multiplied by dV. R is what we call the rate of reaction, which is has the units of mass produced per volume per unit time. So if you multiply this by the volume as well, or the differential volume, you will have mass per unit time. So these are the four terms. So now when we substitute in the equation, you will find that we have two terms for each direction or each dimension. So I have two terms for X, two for Y, and two for Z, and this is what we get. Now we have the mass accumulated is this, and the mass rate of production is this. We can divide everything by delta X multiplied by delta Y multiplied by delta Z. So this is how the equation would look like. The last two terms are now done, and they're very simple now. And now let's take a look at these three terms. Each one of them is the difference between the flux at X plus delta X minus the flux at X divided by delta X, which is the difference between the 2 points where these two fluxes are calculated. And and this is what I was saying about the differential volume, that we have the different. If we put limit of this term at delta X tends to 0, this is going to be exactly the definition of the differentiation. So this is the differentiation of NA with respect to X, NAX of course, and this is the differentiation of NAY with respect to Y. This is the differentiation of NAZ with respect to Z, and then these are the last two terms. If we take a closer look at the first three terms, this is what we define as the del dot NA. So this is the equation for NA in the three dimensions, and the same can be applied for component B in the three dimensions. We can also do the same with molar units or molar units. So for the molar units, it's going to be NA, which is the uppercase N, and then C instead of rho, and the uppercase R instead of the lowercase r, and the same for a component B. So this equation that we see here, or the four forms of the equation that we see here, is called the continuity equation or equation of continuity, and it is the general form of the diffusional mass transfer and can be used at any case. And this is something that we need to check now. So now we are assuming that this equation is the equation that we were looking for, or we were trying to reach, and we need to revisit the conditions that we put before, or the the criteria that will confirm that this is the equation we need. So we had three points, and we we said that this is these 3 points are important, and the equation must fulfill these 3 criteria. So there must be, the first was the time dependence, and we already have the time dependence term, which is the second term of the equation, and the second is the reaction term for production and consumption, and we do have this term as well in the equation. For the third term, it's a term that allows the prediction of concentration at any point, or to get the concentration gradient. This is not very clear from the form of the equation that we have right now. So we will do more checks to make sure that or to see if this point is satisfied or not, and this is what we will do in the coming videos, inshallah. So I'll see you then.